Today we're going to talk about FitM, the fuzzer in the middle, for binary-only coverage-guided fuzzing for stateful network protocols. Us, that's me, Dominik Meyer, and my colleague Otto Bittner. And we work together with two other contributors, Julian Bayer and Mark Munier, both from TU Berlin. Everybody, I think, at this point in time already knows what fuzzing is. Fuzzing means throwing random input at the binary or at the target until it crashes. But there are still some things when we look into reverse engineering and things where you don't have the source code, but you only have a binary, that are still pretty hard. And some of them are servers, where you have protocols that are talked between the client and a server. And this protocol exploration can be pretty daunting. So here you can see a classic a flowchart of an FTP server protocol. Everybody has probably seen this in the past. You have a client that connects to the server. And then after a first initial handshake, the client will send a user. In this case, for example, it could be an anonymous user. And finding out this first interaction for a fuzzer will be trivial. So it's like a very short binary string. It's only 4 characters that have to be random, and then you can set a username and everything is fine. So this should be super easy for a fuzzer, right? You can have like multiple feedback mechanisms to also infer the strings, and you can split up the different compares, like only check for the U, only check for the S, and so on and so forth, to make it easier to brute force this. Now, after the first interaction, the next interaction will be the password. But sending the pass is, again, one further step in the same chain. So what like a random fuzzer like AFL sees is, first you have the first part of the input. Now you have 2 pieces of input. And the fuzzer will only treat this as one single input usually, and you split this up in your harness manually when delivering it to the target. Now, in this case, the problem is that when you flip a bit in the first part in the user, then the target will no longer accept password. So you see, once you flip a bit in the first part, second part doesn't work anymore. It continues on with the third step. After you have the first and second, like you fuzzed it correctly to the place where you can insert the port, suddenly every single flip that will, to find the right port, will be 1 in 3 flips only. So the fuzzer will, I mean, there's some smarts in the fuzzers to try to get around this a bit, but generally speaking, now at this point in time, the fuzzer will have a third only chance to fuzz the right piece that we're interested in to proceed in the protocol. And obviously this continues. This is a very simple protocol, right? FTP has been around for ages. It's not too complex. It's text-based, but you can see here that this gets exponentially harder the further in protocol you get. This is a first, like a big piece of pain that we see in fuzzing for network protocols and like unknown binaries. Then there's other things, like if you would be a reverse engineer and you would try to fuzz something, you would probably have to reverse through the whole binary first and to find like what the target tries to parse. Like there's things that are state dependent. For example, in this case, the password depends on the username. There are things like highly structured inputs. Some things need like a proper checksum set, length field sets, and so on and so forth. And you need to go through all of these manually. Like probably you will see that you're stuck at one different branch in like when you decompile the target or when you look into where exactly you're stuck in your harness. And then you will have to figure that out and get this information somehow into the fuzzer. And then for networks protocols, you have a third big pain point that we saw. It's the execution speed. Like here I have a very stupid, simple example. On the right side, we just built like a socket client interaction that just accepts, reads one int, and then closes the connection again, and does this over and over again. And you see here that doing this 100,000 times takes over 3 seconds alone. You can also see that 99% of the time has been spent in the system, so in the kernel, which is also not really performant. And on the left, just to see like a ballpark figure on this machine. On the same machine, I ran an empty LLVM fuzzer test one input, so an empty libfuzzer input that does nothing, but it gets basically our fuzzer, which is in that case libafl, to generate random inputs. And you can see that libafl is able to crank out 200,000 inputs per second on this machine. So you see on the one side, you have 200,000 inputs per second. On the other side, you have a maximum of 30,000 inputs per second that can actually get delivered to the target via TCP. You can see that this is definitely a bottleneck in our whole fuzzing environment. And then I told you that it's 99% of the time spent in the kernel. And we also know that the kernel scales really badly. So if you want to have this fuzzing on like 128 cores in your machine, then this will get even slower. We only tested it on a single core. Yeah, these are a lot of pain points. To recap the pain points, exploring state spaces gets harder with depth. Structured input generation needs additional insight somehow. And it's a problem if you have an UI or operating system network stack in the middle because it's slow. So what we did was we came up with a novel way to fuzz, which is called FitM, the fuzzer in the middle. And Otto is going to talk you through it.
Yeah, thank you, Dominic. Can you hear me?
Yes.
Okay, perfect. So I'll start off with introducing solutions or our idea of a solution for the three problems that Dominic just mentioned. And the first problem was coverage-guided fuzzers, so that it might destroy the progress it already made in an earlier part. And the solution we propose is snapshotting. That's nothing new necessarily with fuzzing. Many people have done it before, but we feel like it fits very well onto the problem that we're encountering here. And essentially the point where we want to snapshot is whenever we have found a new input for that particular state. And in the example input that we have on the screen right now, that would be after every new line, so every FTP command plus its data. And then the second solution, or the second problem that we had, yes, thank you. The second problem was the input generation. And then the solution that we propose here is essentially in the name of the tool, the in the middle part. So whenever you look at a server, you will always have a client for that server implementing one part of the protocol. And the output that client produces is the perfect input for the server. And so what we are trying to do with FitM is that we fuzz client and server at the same time, essentially forwarding the output of one party to the other party and then mutating it on the way. And the third problem that Dominic mentioned was the slow network stack. And for that, we are patching the QEMU syscall translation layer in order to remove as much kernel code as possible and to speed up the whole thing. So those are the general ideas. And now here's an overview of the technologies that we're using and how everything fits together in general. So in the top part in the middle, you have the FitM itself, and that's written in Rust. And then that manages generally three aspects. So on the left-hand side, you have the client. On the right-hand side, you have the exact same thing, but for the server. And then in the middle, in the bottom, you see the CRIU server. That server is responsible for creating the snapshots on either side of the picture. And that's spawned by FitM whenever necessary. The other thing that FitM does is, if you look to the left-hand side, is it spawns AFL++. And AFL will then, by itself, use QEMU to emulate the client binary and then fuzz it as you would normally expect it from AFL. And then the last bit that FitM does is it collects the output on either side of the picture and forwards it as input to the respective other side. And that's the general idea for the thing. So one one assumption that we generally have with our tool is that network applications are essentially loops of receive, send, receive calls. And on the left-hand side, you have some piece of code from the FTP server implementation where you can essentially see that. So in a loop, the server will receive some command, then handle that command somehow, send out a response, and then wait for the next command. And this loop is what we are trying to fuzz between snapshotting it. So we snapshot at the receive, then we fuzz that part, enter send, and then upon the next receive, we'll restart. And so on the next slide, you will see an implementation model for how we are realizing that. On the left-hand side, again, you have the FTP protocol diagram, and then on the right-hand side is our implementation that is somewhat matching this process. So in the red box, you see the FTP username. That's the state we're currently in, and that's depicted on the right-hand side with the state N boxes. And then on the next slide, you see how the input given to this FTP username state comes from the other side. So the client outputs user anonymous, and that goes as input into the state. And that's depicted by the blue lines. So whenever an input is flowing somewhere, that's a blue line. And now, upon collecting outputs from gen I-1 and procuring them in the current state, then we'll run cmin to minimize the number of inputs we are using for the current gen in order to keep that as small as possible, because we generally have more input than we can handle. So we minimize the set of inputs, then we run the fuzzer as usual, and that works as AFL normally does. And then after a fixed time, we'll stop AFL and we'll collect the inputs that are currently in the queue and run cmin again to remove inputs that don't produce new coverage. And once that's done, we will replay the inputs in order to produce the outputs. So that's the responses that this state would produce for each of the inputs. And we filter those outputs by comparing their string distance and only keeping outputs that are sufficiently different. And the reason for doing that is that we want to remove outputs that only differ in the timestamp or in some random number, like a sequence number or something, because those don't usually produce new states. And then on this slide, you can see the output moving to the upcoming generation, and that's essentially the response. And then on the next slide, you see again with the red bars, you see the state transitions on the left-hand side. And that correlates to to the whole block in gray on the right-hand side. And that's essentially each of the red bars is a receive call. So you receive something, then you produce a response, that's the send, and then you go into the next receive waiting for another input, and that's where the fuzzer stops. Yeah. And then the next bigger component in our implementation is the network emulation with QEMU. And the big thing there is that it delivers input via shared memory to the actual target. And then we remove as much of the kernel code calls as possible. And all of that gives us a pretty big speed up. And then in the bottom, you see the different syscalls that we touched. And we found out about those syscalls by S-tracing different binary targets and then seeing where stuff breaks, essentially. So it's a bit of a trial and error process, but by now it has stabilized somewhat. And then what else? Right. And so we have what we found useful for implementing those patches is that we use a designated file descriptor in order to trigger our patched functionality. So whenever socket is called in our custom QEMU version, a static file descriptor is returned 999, and we call it FitM FT. there are some preliminary checks whether or not socket should return that or return a normal socket. But once it does, that file descriptor can be or is automatically used by the target to trigger the special handling of the hooked functions because they will react to that FitMFD. And then for the receive syscall, again, once receive is called on a FitMFD, we'll have some custom logic that checks if we previously sent. So if we are encountering the second receive in one of the receive, send, receive loops, and then if we are in the condition that we need to create a snapshot, then the snapshot is created and the process is killed. And at a later point in time, when that process is restored, the code will continue to set up the fork server, connect it to AFL, and then take the input from FitM and return that to the program. If we are entering a receive without having without wanting to produce snapshots, we'll just exit because that's usually happening while fuzzing, and we don't need to handle that in any special way because the upcoming snapshot will handle everything that comes after the receive.
Let's see how well this thing works in practice. We used a variety of different tools to test this. We used, for example, a closed source software like TeamSpeak, which is pretty hard to do because there's a lot of inter-procedure calls between different parts of the service. We used a media server, Live 555, and we used also some other services. For example, we did most of the evaluation using the Light FTP daemon, which is also used by AFL-net, a network fuzzer. And we did most of our evaluation against AFL-net. Here you can see some table that describes our tests for a run between AFL-net and FitM. And running for a longer time, 15 hours in this case, FitM reached a greater depth in our calculations. And what is the most interesting thing here is the cut overhead we have in comparison to AFL-net. AFL-net delivers test cases via TCP, and AFL-net will have to re-execute the whole thing from the beginning every time, while we only fuzz a single send receive send loop, receive send receive loop. So even though we have snapshot stores and snapshot restores, in total over the whole 15 hours we got a far higher exec time. And if you calculate it, the speed up is 267x, which is pretty good. And none of the fuzzers found crashes because it has already been extensively fuzzed. However, FitM did find crashes in the client that we fuzz at the same time, which was the GNU FTP daemon. Here you can see the protocols in comparison, or basically how deep the fuzzers get into the protocol according to our evaluations. AFL-net spends a lot of time mutating still, even though they have some smarts about how a protocol works. They still spend a lot of time stuck in the first generation, while FitM continues to a later generation almost immediately, and we fuzz the later stages more. That means we have more state exploration and potentially get deeper into the program. Then we also evaluated how well our filtering works. That Otto talked about, basically the output filtering and we also filter snapshots, so we don't want to take too many snapshots over time because it fills up the disk. Here you can see the dashed line, which is the total outputs that would be able to produce new states if we wouldn't have used gyro Winkler distance to filter them. And the actual blue and yellow lines are the ones that we actually take. So you see, for every generation, we have some new snapshots, but it's not growing exponentially as you may expect from something like this. But actually, the client pretty fast has no more new states to discover, and the server up until the end still has some new states that we find, but it's not growing too far. So yeah, to recap the whole thing, This is, again, the building blocks of our fuzzer. We have FitM that takes snapshots and is able to restore the snapshots. Each snapshot is restored into a namespace that we just do to be able to run multiple instances next to each other, because the server may expect some ports to be open and everything. And also the process IDs on snapshot restore could collide. And then we start the fuzzer inside the namespace. The fuzzer will feed our network emulation layer inside QEMU, and will feed one single receive, send, receive loop, and then is able to fuzz this, and then we collect new snapshots. So in conclusion, we created FitM network fuzzer for network interactions. We fuzz client and servers at the same time. FitM emulates binaries and the network layer, which is really nice. And it uses snapshotting to reach deeper protocol states. And it's fully open source at fg/FitM on GitHub. So this is our time. Thank you so much for your time. And now we are open for questions.